Did you know that there are different types of infinity, and that some of these are larger than others? If you didn't, then you've come to the right place. To test that it's safe, this video was tested on a control group of non-mathematicians, with medical staff close to hand. 8 out of 10 non-mathematicians rated it as interesting. The other 2 are the ones that phoned the police, but that's not the point. The point is that the mention of the word mathematician didn't make you faint with shock. Or even worse, post a rude comment and search for Big Brother videos instead. Good for you. Here's a fairly simple question for you. How do I know that 2 sets of things are the same size? For example, suppose I have a set of babies and a set of chainsaws. How do I know that I have the same number of babies as I do chainsaws? Well, obviously I could count them. I have 1, 2, 3 chainsaws, and 1, 2, 3 babies. Great, so they're the same. But this technique is no use if I have an infinite supply of babies and an infinite supply of chainsaws. I'll be counting chainsaws until I die, and by that time the babies will probably run off and cause mayhem by forming a political party or something. So a more useful way to check they're the same size is to pair up the babies with the chainsaws. As long as I know that each baby has a chainsaw, and each chainsaw is being given to a baby, then I'm happy that I have correctly paired them up, and therefore that my 2 sets are the same size. To make it sound more complicated than it is, mathematicians call this pairing up process a bijection, which has the downside of sounding like the way you'd sedate a rhinoceros. But quite frankly, I call the process of pairing up babies and chainsaws lunch. Our exciting voyage into the utterly useless world of infinity requires a starting point. And that starting point is these, called the natural numbers. They're the numbers you've been counting things with since you were 3, so I hope you recognise them like old friends. We're going to compare this set of numbers with other sets of numbers, and, using the pairing up technique, work out whether they're the same size. Here's a set which consists of all the natural numbers and also 0. Are these 2 sets the same size? Remember that they're the same size if I compare them up. They're only different sizes if pairing them up is absolutely impossible. Pause the video for a few seconds and think about how you'd pair the numbers up. Some people say, well, if I pair up 1 with 1, 2 with 2, etc., then 0 is left over, so they aren't the same size. But this isn't right. All this shows is that you can't do it this way. It doesn't show that it's impossible to pair the numbers up. In fact, you can pair up these sets by matching up 0 with 1, 1 with 2, etc., blah 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 blah. We've found a way to pair up all the numbers, so these sets are indeed the same size. You've probably heard somewhere that infinity plus 1 equals infinity. Well, infinity isn't a number, but that's kind of what's going on here, because adding another number into the set doesn't make it any bigger. Just like spitting into the ocean doesn't really make it any wetter. Well done if you're with me so far. Let's up the ante. This next set contains all the negative numbers too, so it goes down as far as you like. Allow me to introduce you to the integers. So, what do you think? Is this set the same size as the natural numbers? Can you pair them up? Pause the video and think about it. No, really, do it. Don't just run off and have a cheese toastie and pretend you've done it. Have a go. The first time they see this, 99% of people, myself included, say no, the set of integers is clearly bigger because it goes off to infinity in both directions. But this argument is about as convincing as Uri Geller trying to sell you a paper lawnmower. There is a way to pair them up. If you didn't think it was possible, have another go. Here's a way to do it. Split the natural numbers up into odd numbers and even numbers. Now match the odd numbers up with 0, 1, 2, 3, etc. And match the even numbers up with -1, -2, -3, etc. Spiffing! We've done the impossible and shown that the integers are the same size as the natural numbers. Great! Congratulations if you got that one right. If you don't understand why it's the right answer, then try again, but this time with a cup of coffee or tea. Or vodka. Here's a slightly more complicated infinite set, this time a set of points on a graph. You'll have to imagine that the points keep going even off the screen, like a ludicrously massive battleship's grid. This set looks a lot nastier. Each point has two natural numbers as coordinates, so you might look at it and say that the number of points is infinity times infinity, which is enormous! But I already said that infinity isn't a number, so now I'm forced to come round to your house and eat all of your biscuits one by one. It turns out that this set is the same size as the natural numbers. There's a way to match up a natural number with each point. Can you find a way to do it? Pause the video while you think about what you had for breakfast. You might have tried something like this. Let's count through the first column, then the second column, etc. blah 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 blah. But hang on a second. The number 50,000 has been paired up with a point somewhere up in the first column. So has the number 1,000,000. In fact, all of the natural numbers have been paired up with points in the first column. So actually, you missed all of this lot. They don't have numbers. If you tried this one, pause the video and have another go. Here's one pairing which works. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. blah blah until the cows come home. But even if you don't have cows, or if you keep them indoors, by following this snaky pattern, all the points get visited, and every point gets assigned a number. So they are the same size after all. Looks like infinity times infinity was infinity. If you're with me so far, then you're ready for one of the most ingenious and mind-bending pieces of mathematics ever. Here's another set which contains all decimals between 0 and 1. It contains a half, a quarter, 2/3, pi divided by 6, 192 219ths, anything you like between 0 and 1. So what do you think? Can you pair up every number between 0 and 1 with a natural number? Equivalently, is it possible to write them out in a list like this one? Pause the video while your next door neighbours practice their yodeling. Perhaps you tried to list them like this, starting with point 1, point 2, point 3, point 4, etc. Then continuing with point 0.01, point 0.02, point 0.03, point 0.04, point 0.05, etc., etc., and carrying on down the line until you get smaller and smaller numbers. It's a good idea, but think about the number 2/3. Its decimal expansion goes on forever, and none of the numbers on this list will do that. This list misses out rather a lot of numbers. The German mathematician Georg Cantor thought long and hard about this problem, and in 1874 discovered shockingly that the answer is no. You cannot pair up the real numbers between 0 and 1 with the natural numbers. There are simply too many. And if you don't believe me, I'll prove it to you. Suppose you reckon you found a way to pair up all of the natural numbers with all of the decimals from 0 to 1, like this one. I then cruelly stamp on your dreams by doing the following. I create a new number by writing 0 point, and then taking all of the digits along the diagonal. I then change each digit by 1, up or down, it doesn't matter. Take a good look at this number. It's definitely a decimal between 0 and 1. But it's not on the list. It's not the first number on the list because I made sure that the first digits are different. It's not the second number on the list because I made sure that the second digits are different. And so on. It's not on the list. But the list was supposed to contain all decimals between 0 and 1, including this one. So the pairing is wrong and the whole thing comes crashing down like a bookcase bought from IKEA. It doesn't matter what pairing you try, I can always find a number that's not on the list. So you can't possibly pair up these two sets. In other words, you can't list the numbers between 0 and 1, not even if you could keep going for all eternity. Although I reckon that's the second most boring activity imaginable, the most boring being watching snooker, darts or golf for more than 5 seconds. The proof I just showed you is called Cantor's diagonal argument, and it shows that there are more real numbers than natural numbers. If it's driving you mad thinking about it, then be careful, because it certainly drove Cantor mad. He went on to show, using objects called power sets, that there are larger infinities still, and the sheer mind-boggling nature of his work, together with the insults of his critics, drove him insane. He spent the last 15 or so years of his life in and out of sanatoriums until his death in 1918, which is a rubbish way to go for such a genius of a man. If you've enjoyed this video, then don't hesitate to post a comment below or send me an email, and maybe I'll get around to doing another one. But right now, I'm off to deal with the infinite set of chainsaws that somebody's inconsiderately left outside my room.